So slope fields, also known as direction fields, also known as gradient fields. So we have these slope fields of differential equations. So the derivative equals some function, and that function could involve both x and y values, gets assigned to every point in the plane. Let's do an example, it's a lot easier. So how do you create a slope field? I'm going to do y dx is minus y on x. So for every point that we want to do, now obviously it's impossible to do every single point. So I've made mine just one apart in both the x and the y's. Substitute it in. So for the very first one there, where x is minus 5 and y is 5, if I was to substitute in, I'd get positive 1, wouldn't I? What you then do is at every point, you then draw just a little line interval, but at that particular slope. Every single point, we've just basically drawn what the tangent would be doing at that particular point. Now what that does is, if we have a look at it, you get a feel for the solution. So it's sort of like visual integration. Without actually integrating, you get the picture of the shape. So that would suggest, if you look at it, we've got hyperbolas, if you were to follow the slopes. Now how do you follow the slopes? Well, just start at a point and then you head off in the direction of the tangent, and then you keep, so whoop, here we go. There's a whole heap of different ones depending on where I started. And so the actual slope that you've drawn in tells you where to go to. So there's a whole heap of possibilities there. Now, if I want the particular solution of 2, 2, then I would start at 2, 2 and then work out the curve from there. So the particular one for 2, 2 ends up being y equals 4 on x, but there's the particular ones. Now, how is it useful? It's useful for those curves that we can't actually integrate, because we can draw a slope field, so at least we can see what the solution is going to look like. So let's have a look at minus x on y. Oh, that's different. So y on x gave me the hyperbola. X on y, well, what does it look like our shape's going to end up being? Yeah, we're going to get circles. So there's a whole heap of different circles we could get there. Minus 1 on x cubed. And there's the slope field. Now, there's some interesting things to note here. If the y dx is just some function of x, so it's not a mixture of x and y's, it's just x's, notice how the columns, in each column, the slope is exactly the same. And that's because you're not substituting in y. So at each point, you're substituting in the same x value, and you're going to get the same slope. So if you're looking at a slope field, and you notice those columns, then you know that derivative must have equaled just a function of x, but not a mixture of x and y's. The other thing, if you notice you have a continual horizontal or vertical lines, you must end up with asymptotes. So at x equals 0, didn't actually draw in the vertical lines, but we would have vertical tangent there, if you like. The curve doesn't exist there. Right? That's what we end up with. A whole heap of, well, they look like y equals 1 on x squared, doesn't it? Well, that makes sense, I suppose, because if you integrate minus 1 on x cubed, you would get some multiple of 1 on x squared. Okay, y dx is 1 minus y. Now, this time, notice the derivative is a function of y. There's no mention of x. So now, instead of the columns having the same one, the rows are all the same as you go across. Because now the x value is not having an effect on the derivative. Okay. Here is a lovely slope field. Identify any solutions of the form y equals k. So a solution y equals a constant. Well, that would be a horizontal line. So I'm looking anywhere where I consistently, horizontally, the slopes are horizontal. So it just keeps sending me across and I end up with a horizontal line. Well, that happens there at 2. So a solution to this would be y equals 2. Now, it's kind of a trivial solution, because if you look at it, if y is constantly equal to 2, differentiate y equals 2, you get 0. Now, of course, if you make y equals 2, the derivative is going to be 0. So that makes sense. Now, they want us to draw a particular one that passes through this point here, minus 3, 1. All right, I shall attempt. Here we go. So now this y equals 2 must end up being a horizontal asymptote. I'm following it along, sort of, it's telling me to, okay, bend down. I know it's got to go through that point there. So I keep going, down, down. Now, when I come down to around here, these slopes are starting to turn up. So I know there's got to be a turning point here somewhere. It sort of looked like that was horizontal to me, so I thought, okay, that's where I'll put the turning point. And then we'll come back up and go asymptotic again. So, describe the trajectory as x is approaching plus or minus infinity. So what's happening at a plus or minus infinity? That's our horizontal asymptote that we end up drawing in. So y will approach 2, but it'll approach it from underneath the asymptote. If the point I picked was above y equals 2, it would still be a horizontal asymptote, but now it would be coming from above. All right, so let's play with 13b.